Yes, thank you. As our gracious host Mike mentioned a few months ago, we made the grievous error of inviting anybody to come up here and talk about anything. And now you're about to see the results of that mistake. So the reason I'm doing this is because I hear all this hype about quantum computing. It's the greatest, next greatest thing. It does this, it does that. It has all these wonderful features, but I could never get a straight answer on how it worked, why it worked, what's so different about it. So this is my personal journey to understanding quantum computing because I couldn't find a coherent, consistent story anywhere. This is targeted towards a general audience. It will help if you have high school math. But then I realized that when I was in high school, calculus and complex numbers are part of high school math, and not so much anymore. But bear with me, I'm not going to be, there's no test at the end. Without further ado, let's see. Disclaimer, I am not an expert in quantum computing, so anything I tell you could be a lie. It's for entertainment purposes only. Any similarity between a person alive or dead is purely coincidental, and your mileage may vary. Now, Mike wanted me to put in an introductory section here. My name is John Dubois. I'm a physicist, a software engineer, insufferable geek. What's the big effing deal with quantum computing? And there you can see a little picture of a quantum computer. I'm going to cover out what they are, how are they built, and what are they good for, and also what are they not good for? And can I get one to play with? We'll see if that works. But a bit of background. I'm going to need an awful lot of context for this stuff to make sense. The quantum computing actually comes at the end. This will be a circuitous route, so bear with me. I hope I don't bore anybody. You've probably heard all the hype, the superposition, the entanglement, interference, and all that kind of stuff that make quantum computers great. But you really have to know what they mean and how they work together. My goal here is initially to demystify quantum computing. But sadly, by the end, I will have to remystify it because it is completely whacked. And hopefully you'll understand why when I get there. In the beginning, we got to talk about different ways we've done computing. At the very beginning, we used to make analog computers. Does anybody know what this thing is?
Logarithmic scale?
It is a logarithmic scale, but that is a thing called a slide rule. Yes. And you're right about it being logarithmic, is these numbers are logarithmically spaced on here. And you slide the inner one along to match up numbers, and then you slide the cursor to get your answer. So what it basically does is it adds together two logarithms, and you look up the anti-log to get the answer. And that's how they did multiplication. You go, man, that is crude. But you got to remember, that put men on the moon and helped to design the atomic bomb. That's what they used to use back then. And this little thing on the bottom, you got your A and your B, and this calculates the average. So that is a calculator, very primitive mechanical calculator. That didn't last long. Well, it did last long, lasted centuries really. But then we got the electronic versions. So this is an analog computer. It's got an oscilloscope display there, and it's got sliders and buttons and places to put components. It really got interested with electronics because you can do a lot more with electronics than you could with levers and stuff. The basic component of analog computers like this one is called the operational amplifier, or op-amp for short. And you can buy, chips full of op-amps to this very day, and they're still used quite frequently in a lot of analog circuits. The op-amp was just a very, very simple concept. There's a high gain amplifier with high input impedance and had differential inputs. The way it worked is that you configured the op-amp to do various things by the feedback loop you put on it. So an analog feedback loop. So you could get it to do multiplication, addition, differentiation, integration, all sorts of fancy mathematical operations, hence the name op-amp. And this is what they look like schematically. They have an inverting input, a non-inverting input, and an output. 3 terminals. Not very complicated, but if you look at the mathematics below, the A, or the gain of the amplifier, was entirely determined by the resistors. So that means you program these things with resistors. And there's two common configurations, inverting and non-inverting. A simple thing like this, it just corresponds to a scalar multiplication. So if you rearrange the math there, your output is just a scalar multiple of the input. The scale factor is called the gain. And when you put a negative feedback loop like this, which is connecting the output to the negative input, it tends to correct itself or drive itself back into a stable situation. And what it will do is it'll try to make the negative and the positive terminals the same voltage. That's what negative feedback does. And that is how it calculates things. So it computes by just doing amplification. The output voltage is the result of the operation. Analog computers work by making something similar to the problem you're trying to solve. And the voltage here might represent the level of water in a container, and the output might represent the flow rate or something coming out. A single op amp doesn't do a heck of a lot for you. So what we're going to do here is we're going to put them together into a circuit that does multiplication. So we're going to do some math with op amps. Now you see, got 4 op amps in a circuit there. There's 2 inputs, V1 and V2. And the way this thing is these little arrow things are diodes. Okay, and if you know any electronics, you know, oh, we use diodes to make electricity go in one direction only. Well, that's not what they're doing here. What they're doing here is they're being operated at very low voltages before the actual switch on voltage. And in that very small voltage range, they actually have an exponential transfer function, which means that the current going through them is exponentially proportional to the voltage you give to it. So these things are, because with these ones here with the diode in the feedback loop, remember it's a negative feedback loop, so it's giving feeding back an exponential version of the output. So it's actually taking the logarithm of the input. And then this op amp in the middle, I think I've actually got notes on this. But that's not all. Let's do something fancy with op amps. If you've ever done any control work, like motor controls or process controls and stuff, there's a common technique called the PID controller, which stands for proportional, integral, and derivative. If you take any error signal, which is the input to this thing, you want to send a correction signal to your system, which corrects for any overshoots or undershoots or things like that. Mechanical systems will have resistance. Mechanical resistance, they'll have inertia, and then they'll have just a regular error position, right? They can be out. If you can make different combinations of the proportional signal, the integral of the signal, and the derivative of the signal, you can produce any kind of control feedback you need. So by mixing these 3 together, you've got a general purpose controller. And all you have to do is simply set up the resistors and capacitors right. So in this, the integral here, the capacitors in the feedback loop, so that integrates. We've got a capacitor in the feed forward, so it makes a derivative, and that's just a regular scalar multiply. And these all get added together in the middle stage, the summer, and then inverter turns it back around the right way around, because that's an inverting summer. And then you've got your outputs, your correction signal, and that would drive your motor, robot arm, or your pumps or whatever. So it's just programmed with the resistors and capacitors. But here's the cool thing. It executes the algorithm just by balance, just by doing its regular amplifying stuff. Whoops. But it's probably faster than a digital computer. right, is not doing a whole bunch of number crunching. It's just the amplifier stabilize in microseconds, and you get your output, your error correction quite right away. But everything adds up in an analog circuit. Because the voltage is the solution, anything that affects the voltage can get mixed in with your signal. So in this diagram here, the blue signal is the ideal output. That's the correct answer. But we have noise signals like, your vacuum cleaners going, or the streetcar, or you've got radio frequency getting injected into the box. That noise gets added to your output. So that creates an error in your output signal. And then there's other problems, like suppose you have imprecise values of your components. It's hard to make a perfect component. Things like this thing here called the Gibbs phenomenon, that is due to having a finite bandwidth of your amplifiers. Your amplifiers can't respond instantaneously. Another problem is if you had a very high bandwidth system, it would become unstable anyways, because it would feed back, radio frequencies back into your audio frequency signal. And you can't get rid of all noise. If you got a really, really perfect circuit, you get down to the very minimum is what's called shot noise. Shot noise makes a sound like pouring marbles on a plate or something. And that noise is caused by the individual electrons going through the circuit. So there's practical limits to analog systems. That limits where they can be used. Well, then comes digital computers. So the first ones weren't even electronic. If you ever see old movies where they pull a crank on the adding machines to make all the gears turn. But the difference with electronic computers or digital computers is that the lever position, the voltages, water levels, or whatever they are, they don't represent the solution. They represent an abstraction. And the abstraction here is we're gonna interpret them as numbers. Commonly, we use binary digits or bits, where you take the B and the its and you get bits, and we interpret those as 0 or 1. Now, that's not the only abstraction we can use. In fact, there are people that put a lot of effort into trinary systems, where they have levels like 1, 0, and -1, what's called a symmetric trinary system. But I think the reason they weren't so popular is they didn't choose the right name for their digits. They didn't take the same pattern. And I'll let you do the math on that. They're just fancy calculators. And you see in this, the little computer on the side here, that's an old Data General. And put this one up here because it shows you the bits. And those old computers, each one of these lights represented 1 bit. Or this is a word of address that's across the top, and this is a word of data across the bottom. And they had little switches. You can actually go and set individual bits in the computer's memory. But the other cool thing is they were software programmable, which means you didn't have to put wires, change your resistors or capacitors if you wanted to run a different program. So how do digital computers work? Well, they work completely differently. They use math. And they use a math called Boolean algebra, which is the mathematics of things that can only go to 0 or 1. And you'd combine them, and unlike the multiplication and division stuff that we use for base 10, they would have simple operations such as not, which is in this table here. If you put in the input is 1, the output is 0. So it's just the opposite of the input. An AND gate can take 2 or more inputs, and it's characterized by giving you a 1 only if all the inputs are 1. And then an OR operation is characterized by giving you a 1 if any of the inputs are 1. And then there's a combination operator called an exclusive OR, which gives you a 1 if only one of the inputs is 1. But with this very basic set of operations, you can do an amazing amount of calculation. And I've got down there an expansion of XOR, which you can do with the other gates. In fact, you can do all of this with a single gate, a single NAND gate. You can make all the other gates out of NAND gates. It just requires more gates. Because this is now a mathematical construct, you can do, of course, math on it, which means you can take complex equations or expressions and simplify them. So you don't have to build complicated circuits. You can get out your pencil and paper and reduce it down to the minimum number of gates. And you can see that there's a bunch of, just like we have identities in trigonometry and stuff, there's identities in Boolean algebra. Like the A XOR B is just equal to B. And then, of course, Boolean algebra has its own operator precedence, just like we do with multiplication and division and in addition. And again, you can do fancy math on it. There's a very common construct called the De Morgan's theorem, where you can say not A and B is equal to not A and B, or A and not B. So you can simplify expressions doing that. Being able to write math makes it a lot more useful. So what do we do with these gates? Well, we can make circuits with them. This is a very important circuit here. This circuit adds 2 bits together to produce a sum. It's called a full adder. It's a 1-bit sum, and you'll see that it has 1 output bit and 1 carry. So you have to string these together if you want to add big numbers together, because it's pretty easy to add 1 and 1. So we want to do more important things than that. And notice that when you chain them together, 1 bit can affect all the other bits down the chain. Now, if you have a big long set of these, like 32 of these or whatever, if the last one produces a carry, that means it's overflowed the capacity of your adder. Now, to make bits useful, we collect them together in groups. 8 bits is commonly used in the old days, and you've probably heard of 8-bit graphics. That's because we only used 8 of these things. So 16 is a common integer, 32 is a typical larger integer. Does anybody know what half a byte is called? Yes, it is called a nibble. Now that made me think, what would if they have a special name for pairs of trinary digits? The other thing I should mention, sorry, I'm getting a little off topic, but bit has a special place in information theory. It is the smallest unit of information you can have. Anything can be broken down into the number of bits it's required to represent it. So you've heard of things like 16-bit audio. That's because they figure that any additional bits is not going to give you anything more useful. 32-bit graphics, you have to figure out the trade-off between how many bits to represent something, because each bit is expensive if you need to do something more with it. In hardware, when we have collections of bits in hardware, we call it often a register. It's just a place to hold a collection of bits. So that's just some terminology for you. But here's the big advantage of digital computers. The key is the abstraction. The voltages are not analogous with the solution, so it doesn't represent the answer you want. And that's why I put this little voltage scale over here. As you can see, that at 0 volts all the way up to 0.8 volts, we're going to call that a 0. Doesn't matter where here it is, it's going to be a 0. It could be a dirty 0 or a clean 0, but it's still a 0. And all the 1s are up in this area, and there's a no man's land in between. So there's no ambiguity between 0s and 1s. You can't have something that's almost 1, but not quite. Right? And that's what allows digital computers to be perfect, because it's very easy to get your electronics to hit those targets. But you saw how many gates it took to add 2 bits together. We do a lot more than that with computers these days. Things get complicated. In the old days, if you wanted to multiply 2 things together, you would have to do an addition, and then you'd have to shift it over and then do another addition and add those together and then shift it over and stuff. So it took several steps to do a simple multiplication. Modern computers have dedicated multiplier circuits. that do shifting and adding and stuff almost all together, but it still requires a few steps inside the CPU. And these steps are governed by the system's clock. There's the clock that keeps step of all the parts of the digital computer. But it still takes a few steps. And these are controlled not by program code, but by something called microcode, which is built into the hardware. Some of the old mini computers, you actually could program the microcode and reconfigure your CPU by changing the microcode in firmware. But as an example, the add, subtract, multiply, those are machine instructions. That's the lowest thing you can program. They take 4 clock cycles, 4 cycles of the system clock. But a division can take 11 to 26 clock cycles. This tells you that a division is a lot more expensive than a multiply. So if you can rewrite your algorithms to use multiplication instead of division to solve a problem, then you can recode things. Now, consider the integration and differentiation that we did with that PID controller that did it in microseconds. We're gonna take several clock cycles to do that, and to do that we use a software algorithm. Now I have on the side here. Let me see if I've got it. Okay, on the side here I have an algorithm. This is a very important algorithm called the quicksort algorithm. It's very common in the computer to have to sort numbers or words or whatever, and they all will use some variation of quicksort. And the reason I want to point out a few things about the quicksort is this one shows you moving individual elements of the sort. But the really important thing is this is the quicksort algorithm, and it calls itself twice. And this is called a recursion. And what it does by doing this recursion is it splits the problem in half every time it calls itself. You'll get, the first time you'll take this initial array, divide it into half, and give each half back to itself, and that'll divide that in half. And that does a little bit of flipping each time it does that, and that's how it sorts itself. And because if I gave you a stack of cards and say, put these in order, you're probably going to go through a much more complicated, well, probably a simpler procedure, but it's going to take you more steps. The number of steps you take is called the time complexity, or the amount of time it takes you. Also, you can trade off space complexity, which is you can take up more space. And quicksort does a little bit of trading off there by creating a new stack element every time it calls itself. So it takes up a little bit more space, putting these into smaller piles. But time complexity is what we're really worried about here. How long does it take to get the job done? Let's take a look at complexity. So what is the big deal with complexity? Let's consider this unordered list I have over here. This is just a sample of 11 names. Our problem, suppose we're the computer or the programmer, our problem is we have to find out if Maggie is in this list. How do you do it? You have to step through each one and look. Is there any other way to do that? No, there is not. This takes, on average, n/2 steps. So if you've done this a million times and you're searching for a name in the list, on average, it's going to take about n/2. So this, in the jargon of computer scientists, this is called an order n algorithm, which means it scales as n scales. So if you have twice the size list, it takes you twice as long. The computer scientists are very interested in how problems scale. That's just how they characterize complexity. Double the number of elements, double the length of time to get a solution. The quicksort algorithm we did on the previous page has the complexity of order n times log n. If I gave you a deck of cards and you sorted them on your desktop or something, you'd probably be n squared because you have to go through a couple times to get everything sorted. And because the quicksort is clever enough to divide its problem in half each time, that gives you the log n factor. So it's less than n squared. So that's why that algorithm is important. Now, instead of writing the code out like I showed you there, we could also do it in a flow chart. This is another way of representing an algorithm. So most people have seen a flow chart someplace in their educational history. It's just a graphical representation. This is the actual graphical representation of that search through an unsorted list. And when you talk about complexity, scalar factors of 10 or 5 don't matter. So I won't bother explaining the flow chart and all the different symbols there. Okay, let's talk about levels of complexity. And this is where all that complexity talk comes into play. This is the graph of all, well, not all possible, but common complexity scales. So along the bottom is the number of elements you have to work with. So a number of names in the list, number of entries in a database, number of bits in a number you're factoring. That's the elements. Operations is the number of steps it needs to solve the problem. So let's take a look at some common complexities. Log n or binary search is very easy because if you have this stuff already sorted, it's much easier to find the answer because you can jump in the middle and know whether you're gone too far or not, right? And then you can jump back halfway and then you can jump another quarter way. So that goes log n because you're cutting the problem in half every time. And you can see that order 1 and log n way down here. So bring on the elements. I don't care. We can handle it. We'll just chew through them quickly. Okay, the faster the computer. Now, we talked about the order n, which is quite reasonable. If you have 1,000 things, you expect it to take half the time of 2,000 things. That's reasonable. Just like someone quoting on your house, how much you want to paint. The house is twice the size, you expect it to be twice as much. Manageable, right? And you see that little, and you see it scales quite readily there. And then we have, well, there's the n log n in the nice orangey thing. That's our quicksort. Now we get into up here, it's getting into the red. There's the order n squared we talked about. So an n squared complexity might be you have 2 unsorted lists and you want to find the elements in one that are also in the other one. So now your complexity is n by n. Quadratic is starting to get hard. So it shoots up pretty quickly. So if you get really large elements, it becomes intractable. So we want to avoid n squares, but then the general class is called n to the k, which includes n to the 1, n to the 2, n to the 3. Polynomial, call it polynomial time, is something you can handle with a big honking computer. So that's something we can possibly do, but you see, it does tend to go up pretty quickly. But then we get into order k to the n, where the n is in the exponent. This is called exponential complexity. And you can even go worse than that, which is n factorial complexity. So that's a very complicated and time-consuming algorithm. So what's the solution? Okay, well, spoiler alert, we know what the solution is. So we can divide all the problems that we'd ever have to do into this little Venn diagram here. P are the polynomial ones, n to the 1, n to the 2, n to the 3. Okay, but what we're really worried about is that stuff outside of P, that non-polynomial stuff. These are very difficult problems, such as factoring large prime numbers. You have to do that division. Remember how expensive division was? You have to do the division and keep trying and trying and trying. These algorithms take for frickin' ever. And that's actually, we're using it to our advantage right now in cryptography and stuff by making very large prime numbers as the keys for things. Okay, now an important thing to notice about solving non-polynomial problems is once you've solved them, the answers can be very easy to check. Imagine that you've factored a large prime number. You want to check it? One division, done. It works. Spoiler alert, the answer is quantum computing. How does this factor in here? So computers, quantum systems solve very complicated problems very quickly through natural quantum mechanics. So we want to harness their ability to do stuff for us. Okay, but so yeah, we hear this about quantum mechanics. It's not the quantum mechanics that makes it fancy, because quantum computers already use quantum mechanics. Quantum mechanics makes transistors transist and flash memory flash. We're doing something different now. Take a little bit of a side track here. How is a quantum computer made? This is the sort of the aha moment for me. A quantum computer is actually very much like an analog computer. We're using a physical matrix of some type to do the calculations for us. Okay, like our op amps, like our levers, like the slide rule. So we need a physical system, but it has to be a quantum mechanical system to do the computations. We'll call it the quantum matrix. Now, quantum systems are, remember, they're the physics of the very tiny stuff, very delicate. So a quantum system has to be completely isolated from reality. So we want to think of them not as a full-blown computer, but as a quantum processor, like your graphics card or something, where the main computer does all the setup and all that kind of stuff. We hand it off to the graphics processor, and it does all its computation, and then it goes back to the computer with the answer. That is what a quantum processor, a quantum computer actually is. And like your digital computer, it also uses an abstraction layer. So it's kind of a hybrid of analog and digital, because the quantum systems we build, the little analog boxes, the external quantum matrix, we choose them to have exactly two quantum states. You probably know that like atoms and stuff are quantum mechanical, and that's what gives us the spectrum and stuff, but they have an infinite number of quantum states. No good for computing. So we want something that only has two states, and we're gonna call those states 0 and 1, so it looks like bits to us. And their name, the digits, are called qubits, or quantum bits. We use that naming convention again. An actual qubit has to be manifested as a quantum mechanical entity. And those could be electrons, atoms, photons, any kind of quantum mechanical thing, but they're all very small, very fragile. They can be any other physical, there's lots of different approaches to that out there. In order to go forward here, I am going to take one abstraction or one model of a quantum element. So I'm not going to talk about how the other ones are all made to act the same. Let's talk about a property like spin or polarization. Let's talk a little bit more about how they're built. The quantum computers are very fragile. So you'll see there is a sort of a cutaway of what a quantum computer, or one type of quantum computer is. Because anything that affects the quantum element will cause it to decorrelate. The quantum processor is this little guy down here. The rest of this is just support infrastructure. That's just so that this little guy can do its quantum thingies. One photon of heat, vibration, anything will cause it to decorrelate. Okay, so they're kept in the dark and extremely cold. So they're at high vacuum. You can't have any molecules bump into these things. And they're at extremely low temperatures, 0.02 Kelvin. That's almost at absolute zero. The little tubes, you don't have wires attached to these things. There's these little tubes, if you can barely make them out here. Those are microwave guides, and they send radio signals down to mess around with your qubits. And they often refer to this as a chandelier. And each level is colder than the previous level. So Up here at the top is room temperature. And then you might have liquid nitrogen here. And then that makes it cold enough that you can have liquid helium down there. And then somewhere in here, we have what's called a dilution cooler, which is a really funky quantum mechanical device to get really cold, because refrigeration at those temperatures is tough. Like I could do a whole hour on the physics of helium. And the reason I use helium here, I don't know if anybody knows why. Helium is the only substance that is liquid at absolute zero. And that's why they use it for the refrigerant here. And the dilution cooler actually has to use 2 different isotopes of helium to make it work. So very crazy stuff. All right, the humble qubit. Finally, we get to the core of the matter here. This is an abstraction. This is the way it's often represented, although it probably never is something that looks like this. But for mathematical treatments and abstractions, this works just fine. We can do all our math on here, and we can use this to conceptualize what a qubit does. So we're going to talk about, suppose we're going to use spin here, which is the most analogous quantum property here. So imagine we have an electron or an atom that's spinning around. It's got a charge to it. So if you spin it, it's going to have a magnetic field. And that magnetic field, suppose we put it in an external magnetic field, put another magnet around it. What's it going to do? It's going to be like a compass needle. It's going to point with the field, or because it's quantum mechanical, you can force it around and have it go exactly opposite the field. And that's also stable or metastable. But because it's a quantum mechanical system, it can't snap back because that would require it to emit energy. And it can't do that unless it's something has knocked it. This is our 2-state quantum system. It'll either be up or down. And you can see, and they've used the x-axis to represent up and down, but this is really not up and down gravitationally. This is up and down the magnetic field. And we call that one a thing that looks like a 0 and something down here that looks like a 1. Okay, so those are our 2 qubit states. And it is the basic unit of information for quantum computers, like our bits were the basic unit for digital computers. We can flip these things from up to down by injecting energy into it. So we can spin them up or spin them down. They're completely isolated, so they can't change state on their own. And what we can do is we'll interpret one state as 0 and one state as 1. Now, this is superposition. This is the one hype word that you hear all the time. What the heck is superposition? Well, I've got my picture of a classical bit and a picture of a qubit there. They look kind of similar, but qubits are the original non-binary. They can be anything between 0 and 1, and they do it with elegance. So you'll notice that I have drawn not a circle, but a sphere there. A superposition is a combination of 1 and 0. But it's not just a simple combination, right? Because if it was just a simple combination, I don't need a circle. I don't need to go around like this. But this is a sphere. So what the heck's going on there? That is because superpositions are actually complex numbers. I mean, having a real and imaginary part. Now, something important about superposition is we can put our qubits into any superposition. And you can see there's one over here, which is a combination of the 0 state and the 1 state divided by √2 to normalize it. But we can, if we measured something in that state, what would we measure? We wouldn't measure a √2. We'd measure either a 0 or a 1, nothing else. You can only, when you measure it, it'll only be one of those 2 states. The superposition is something we can never access directly. Qubits can also be entangled. Now, entangled, what that means is become part of the same quantum state. It's like being part of a family or a group or something. But what happens is when they're entangled, one qubit depends, or one quantum element actually determines, or not so much determines, but if you know what one element is of an entangled pair or complex, you'll know what all the other ones are. That's why I say one for all and all for one. In fact, the way you entangle things is the way you write quantum algorithms. You have to have entanglement to do anything useful with quantum computing. Now, there's no classical analog to this. It's hard to explain. Okay, and once you measure any part of an entangled system, everything's measured, it's collapsed, and it's no longer entangled. Okay, you only get one chance. And any interaction constitutes a measurement. So let's revisit our order n time complexity algorithm that we did. Remember that unsorted list? Quantum computers, using a quantum algorithm, like Grover's algorithm, we can take the complexity of that order n problem and reduce it to order root n. So that's a huge speed up.
That would be inconceivable. It's inconceivable. Inconceivable. Inconceivable.
You keep using that word. I don't think it means what you think it means.
Inconceivable. It's inconceivable.
Yes. How the heck do you get that down to root n? We looked at the algorithm. It's pretty simple. There's no way around it, unless you're a quantum mechanical particle. Yes, classically, this is inconceivable. So quantum algorithms, if you remember my complexity chart, quantum algorithms make the impossible possible. Shor's algorithm is used for factoring numbers, and we'll talk a little bit about it in the future. So how is this even possible? It doesn't make any sense. Let's see. Can blame this guy, Richard Feynman. He was the guy that kind of thought about quantum computing back in 1982. Maybe, I don't know this for sure. Maybe he got the idea from Feynman path integrals. What the heck is that? In order to explain that, I'm gonna have to take another detour. Sorry about that, guys. Let's go to this WTF moment. This is one of the most famous experiments in physics. It's called Young's double slit experiment. So what we've done here is there was a big dispute about, is light a wave, is light a particle? How do we know? So this experiment was done to try and prove that light is a wave. And if you look at it, it makes perfect sense. We have waves coming in here. We block off a bunch of them, and they have little point sources. So waves radiate out from here, and waves radiate out from there. And if you go straight on target, the crests line up because they're going the same distance, and they reinforce and they make this bright band right in the middle. And if you move off to the side a little bit, they get out of step and you get a dark patch. And then if you move a little bit more, you get a bright patch again. Thomas Young is going, in your face, Newton. It's not corpuscles, it's waves. Huh. They thought they were pretty smart. Well, you can do this with water waves or something like that. Now, if you did this with particles, like baseballs or something, you'd expect to get two piles on the other side of the slits. So that's what they say, not two piles, it's waves. So it makes perfect sense for light waves and water waves. But guess what? You get the same phenomena if you shoot electrons through here. And we know electrons are particles. Come on. We can put on a single electron on an atom. What the heck's going on here? So let's try and be tricky. Let's take a light source or an electron source, and we'll turn the intensity way, way down. So you only get one photon or one electron coming through. What do you think you'd get on the viewing screen? Would you get bands? The answer is you get a dot. a single dot saying, damn, it looks like a particle. But we know it's going to be a wave. Let's put 2 in. Get another dot, but it's in a different spot. And you put more dots through and you keep putting in, and guess what? You get dots all over the screen, but the dots happen to fall more frequently in the bright bands and less frequently in the dark bands. You go, wait, I know they're particles because they're making dots on my screen. So what the heck's going on here? So although the dots can appear anywhere on the screen, they're more likely to show up in the bright bands. When we did this with waves, we called it interference. When 2 waves got together, they made it brighter. When they were out of step, they made it darker. It's still called interference, even though it's particles. The wavelength of an electron is given by this formula. That's a de Broglie wavelength. So what's going on here? I don't know if anybody recognizes that spaceship. Can the electron or photon somehow know there are 2 slits? This spaceship is the heart of gold from the Hitchhiker's Guide to the Galaxy. I don't know if you've ever read that book, but the reason I put it in here is because the sales brochure for the spaceship says, the ship passes through all possible points in the universe almost simultaneously to avoid all that tedious mucking about in hyperspace. So that's how it got around. But this is actually what's happening to our electrons. The Feynman path integral is a way to calculate that wave function by adding up all the possible paths through all space and time to get to the answer. What I want you to do now is look at my double slit experiment in a new light, pun intended, and imagine that it's a question you've posed to the photon. You're saying, hey, photon, find me the best path to the viewing screen. And the one photon's going to go, this one's the best. And another one's going to go, this one's the best. Okay, and they're going to make those little dots on the screen. We're doing quantum calculations with that double slit experiment. And the question is, what's the best path? The quantum system is solving its wave function by navigating all possible solutions at once. This is how we get n squared out of an algorithm, out of an unsorted list. Because it's not doing one at a time like we have to do. It's going, oh, I can see them all. Okay, this one. And that's why we want quantum computings. Wave functions are spread out over space and, it turns out, time. There is an equivalent to the double slit experiment where they interfered 2 photons, but they're separated in time rather than space. And they do this by switching one of the photon beams on and off. And the funny thing that happens is the interference pattern occurs before the second photon arrives. Quantum mechanical systems can do stuff we can barely even dream of. I'm in, we're going to build a quantum computer. Let's do it. Okay, this is, remember we did flowcharts? This is a flowchart for a quantum computer. It combines qubits together and orchestrates their interactions. Here's the explanation of this thing. Here's a quantum circuit. These are the qubits, Q0, Q1, so we've got a 5-qubit machine here. These are the timelines or the operation lines. So this is our flow chart. We're going this way in time. And these things, remember we talked about logic gates? These are quantum gates, H and T's and stuff like that. And when you see something crossing between two qubits, that is a multi-qubit gate. And that's how we get entanglement. A little bit more on that. Quantum gates, what the heck is a quantum gate? We know what a logical gate does. We know what ions and ors and stuff do. And here I am back with my sphere. And this little phi thing here, or psi thing, that is our superposed quantum state. Quantum gates are, I say spin doctors here. They move the qubit between different superpositions. So the wave function is always a point on this sphere, which is called the Bloch sphere. The quantum gates do their magic, their computation, their algebra. They do it by spinning that little vector around. Well, we'll get to some of those gates in a minute, but a superposition is mathematically represented like this. So that's that there mathematically psi equals alpha times the 0 state and beta times the 1 state. Now, in order to navigate the entire sphere, alpha and beta are complex numbers. So the real numbers move us around the any place in the YZ plane. Real numbers will put us there, but if you want to move in any other plane, you need a complex number which rotates around the Z-axis. And the way we calculate probabilities is this thing here called the Born rule. And I'm not going to bother going into that unless you want me to. Okay, let's talk about the X gate. What does it do? The X gate rotates pi radians, which is 180 degrees. It's also called the NOT gate. If I rotate my 0 state 180 degrees, where's it going to be? It's going to be at the 1. So it's basically inverted it, just like our NOT gate did for the Boolean algebra. And if you rotate it again, take the 1, it rotates, it goes back. So a NOT is its own inverse. Now a Y gate rotates around the Y-axis. And if we take a 0 or a 1 state and rotate around the Y-axis, it's going to do the same thing as a X gate. It's going to have it point to the bottom. But that's not all we do with these kind of things. Suppose we rotate something halfway around the X-axis and then halfway around the Y-axis. It matters what order you do them in. That you get a different result. So the Y-axis can act like a NOT gate as well. Okay? And if we rotate around the Z-axis or the Z gate, it basically does nothing to a vector in the 0 or 1 state. So a little bit of a notation so you can talk to a quantum computerist, quantum programmer. We're using a thing called the Dirac notation. Dirac was a famous physicist who did an awful lot of breakthrough physics. And he used symbols like bar A bracket is called a ket, and the B there, that's called a bra. And you do an inner product like this, it's called a bracket. He was trying to be cute. But that's called the bracket notation. And you'll see quantum programmers using this all over the place. So you have to do that inner product thing in order to get probabilities out. Alphas and betas are only probability amplitudes. And I think I talk about that a bit later. Now, this is a bit of math here. These quantum states are orthonormal, which means that one state multiplied by itself is always going to be a 1, and one state multiplied by the other state is always going to be 0, which means they're basically think of them as being at 90 degrees. Orthonormal means the magnitude is always 1 and they're perpendicular, basically. And then we get into more complicated quantum states, and this is called tensor product. And if the tensor product of 2 qubits gives us a combined state. So you'll see you got the bar and then 2 zeros, which means we have 2 qubits, both in the 0 state. And there's a matrix representation for all this stuff. I warned you there's going to be math, okay? Quantum states are also called vectors or state vectors. If you know matrix multiplication and matrix math, this makes sense to you. But they can also have phase, and the phase is usually a complex factor. So operators like gates or functions, and all this stuff is basically matrix math now. Let's take a look at this in more detail. All right, there's a bunch of common quantum gates. Way up at the top, we have the X gate we're talking about, but there's a short form for it, which is a little plus sign in a box. And there's the matrix representation of it. There's a Y gate, and it looks kind of like the X gate, but it uses imaginary components because it's rotating around a different axis. And the Z gate, well, anyways, we're not going to go through all of these. But down here, This is a controlled NOT gate, which means, or if this qubit is a 1, then it's going to not this one. So it's going to invert this one. And now we've got 2 qubits involved, but look at the matrix has gotten 4 times as big. And similarly here, a controlled Z gate. So again, it's bigger. Now, here's one. We've got 3 qubits involved, and look at the size of that matrix. Yeah, it's getting pretty unwieldy there. So that's why they use Dirac notation. And we'll let the computer sort out the rest of it. So mathematical representation. So I explained all that stuff. Oh, there's a swap gate there. The swap gate can be, just like we expanded out the XOR gate by using simpler gates, the swap gate can be expanded out using simpler gates as well. Now, important thing about quantum gates is they have the same number of outputs as inputs. And they also happen to be reversible, which is different than our digital ANDs and OR gates. Now, here's the kicker is you need an awful lot of qubits to solve any real world problems. And complex operations are collected together in subroutines or oracles or whatever you want to call them, so you can reuse them. The important thing is, how does this all scale? Right? Remember, complexity scaling was our big nemesis. Well, let's take a look at an algorithm that uses an awful lot of qubits. If we have 1 qubit, remember it represents possibly 2 different states. If we have 2 qubits, it represents 4 possible states, and 3 qubits represents 8 possible states. Guess what? We're getting exponential scaling with these qubits. And that is going to give us some leverage when it comes to those exponentially hard problems. Notice you're seeing that H gate a lot. Well, we'll talk about that shortly. So this gives us access to those problems which are computationally difficult or impossible. For example, Shor's algorithm takes that exponential problem, order k to the n, and reduces it to something that is order log n cubed. So log n times log n times log n, which is way faster, especially when you get to huge numbers. Now, we're talking about the scaling things. Imagine having a 32-bit register can represent over 4 billion possibilities. So let's talk about that H gate. You'll see it all over the place. And the H gate is important because it's the halfway there gate. It's an equal representation of the 0 and 1 states. If you're doing something computationally with a lot of bits, you want to start off with something that could be either way, could go either way, right? Equally. So the Hadamard gate is used all over the place, halfway between 1 and 0, and it uses that square root of 2 to normalize so that when you do the computations, your final result always has a probability of 1. If you measured something that's been hit by the Hadamard gate, it's going to have a 50% chance of being 1 or 50% chance of being 0. So if I took a Hadamard gate and applied it to a qubit, and then I did another Hadamard gate, what do you think the output would be? Yeah, it would be the same as the input. The Hadamard gate, it's its own inverse. It's like the NOT gate, but in between, if you measured it in between, you'd have a 50% chance of 0 or 1. Something doesn't always add up here. Let's try doing something simple. I showed you how to add 2 numbers together using various other techniques, analog amplifiers, digital circuits. Let's add 2 numbers together in a quantum computer. We could simply recreate the logic, because we know how these gates work. We could do a classical implementation on a quantum computer. Kind of pointless because it's massively expensive and very slow to set these things up. So why would we do classical addition? Let's do quantum addition. So this is the algorithm for doing addition on a quantum computer. So we take the bits, we're going to add together A and B. These are only 2-bit numbers here for illustration. In order to add them together quantum computerly, we would take the quantum Fourier transform of the one number. Now, what the heck? A Fourier transform, I don't know if anybody knows what the Fourier transform is, but it basically takes amplitudes like of a sound wave or something and converts it into frequency components. So we're transforming this amplitude of bits into its frequency components. And then we do a bunch of conditional stuff using the other number that we want to add together. And then we take the inverse Fourier transform to get back to the result. And this relies on the handy mathematical identity that the Fourier transform of A plus the Fourier transform of B is equal to the Fourier transform of A plus B. You go, yeah, why? Why did we bother to build a quantum computer to do that? That is a really hard way to add two numbers together. And this would be much better done on a classical computer. That's why we have division of labor. So quantum computers are not a replacement for classical computers. It's a waste of time. So let's look at some of the good stuff. Let's look at something that's only possible using a quantum computer. Shor's algorithm. Remember, that's the one for factoring numbers. Part of the Shor's algorithm is done on the classical computer. It has to be rejigged so that we can do the hard part on the quantum computer, and the easy part we'll do in the classical computer. We take a bunch of these bits here, we spin them all halfway around with the Hadamard gate, and then we do a bunch of manipulations. And this here is the number you're trying to factor down there. So the number you're trying to factor down goes there. We have entanglement across the qubits and the other row of qubits. This is called the quantum phase estimation phase. So it's part of the algorithms. It's doing stuff that quantum computers does well. At the end, you see it has an inverse Fourier transform to get the results. And these little doohickeys at the end, these are the measurement things that I kind of left off my other diagrams. So the measurement thing, what it does is it measures this qubit and turns it into a conventional bit. So what you get out of this end is a binary number. And if you're lucky, it happens to be one of the factors. Well, or related to one of the factors anyways. You can see that if you're factoring large numbers, you need a lot of qubits to do it. It only identifies one factor at a time. There can be lots of factors involved in a large number. In order to get all the factors, you have to run the system multiple times. And remember when we built up those ridges in the double slit experiment with interference, you go and look for the numbers that come out statistically more than other ones. And then remember I said you could invert these things very easily. You go and divide it back into the prime number, or back into your number you want to factor. And if it works, you go, yeah. Artificial intelligence involves sorting through lots and lots of stuff. If we have things like multiple possibilities, some key takeaways, the quantum computing matrix needs to be highly isolated. So they're very difficult to build and maintain. We need lots of qubits to be useful. And it's not easy to program these things. Okay, we have to be very careful to avoid decorrelation, which will produce a meaningless result, just like our analog circuits. If you got noise in them, it's crap. Now, each one of these qubits is its own quantum system. So you've got to keep it isolated. And the more qubits you add, the harder it is to keep them all cool. And you have to run algorithms multiple times because remember, they're all probability amplitudes. They're not guaranteed results. Current quantum computers are a long way from practical use, but you can see they've made an awful lot of progress figuring all this stuff out. And there we go, we've made it. I mean, that's what brings me to this next thing. For all the really geeky people there, I do have a bonus round. but that's only for people who want to stick around and talk about it. Took a big risk here. Where's my escape? And this is one of the questions I didn't answer at the beginning, which is how can I get one to play with? This is IBM, one of IBM's quantum computers. They have public access sites, and I can go and write a quantum algorithm on here and try it out. I can go and I can drag a Hadamard gate over here, and I'm starting to write an algorithm, right? And you know what I want to do? Actually, I want to put a NOT bit over here first. Okay, and if you look down here at the bottom, what it's done is it's run 100 shots, or it's run this algorithm 100 times, and I've got 50% of each. This is the kids version of quantum computer interfaces. You actually write your code in Python and big, long, honking algorithms. But I just wanted to show you that you can actually go and program a quantum computer yourself if you're interested. Yes, yes, you can actually, I don't know if it's running on the simulator right now. I have to look at it more closely, but you can write your algorithm, send it to the hardware, that big fancy gold chandelier. It'll run it on the quantum computer and give you back the answers.
Where is it physically located?
They're not the only people that do this. Okay, IBM, there's some other companies that have public access quantum computing portals. Microsoft has a Q# language, which is a language for programming quantum computers in. And they also have an interface where you can go and run your programs. Nobody asked me about how wave functions collapse.
Do we know why they collapse when they are being observed? Some people think that's the proof of the simulation theory.
Well, there's no classical equivalent to wave functions and superposition and stuff collapsing. But if I had to describe it, it would be thusly. Imagine you're a quantum system and your wife or girlfriend says, "Do these pants make my butt look fat?" Immediately in your head, you have thousands of imaginary possible answers. That's a superposition. But you know, as soon as you say one word, that's going to be reality. You can only make one answer. And that is when the wave function collapses and you say yes or no. And that's reality. That's when it becomes real. That's how they convert the complex numbers, imaginary numbers, into real numbers.
And yeah, thanks, John. This was, it was extremely entertaining and definitely took me way beyond my limit of comprehension, but that's cool. So thank you.